All right. Well, good afternoon, everyone. My apologies for not being on video. My video is being uncooperative today. But for those of you who may or may not know who I am, my name is Dr. Joni Rixodi, and I am the director for the UCI Center for Statistical Consulting. And I'm joined by a couple of my staff members. You'll see Faraday and Kate Kirby. And I also supervise or direct a unit over in the ICTS, which is the Biostatistics, Epidemiology, and Research Design Unit. And so we are here to support you in your academic endeavors, whether that be statistical analysis, study design, support for grants, manuscripts, all of that fun stuff. And so part of our mission is to make sure you all are well equipped to do the work of your research, to do data analysis, and be able to use software effectively. And so this is part of our monthly Stata workshops. We are joined by Dr. Chuck Huber, who has worked for Stata Corp for a long time, as well as been a faculty member himself. He is fantastic for those of you who have probably heard him present. And he does these for free for us to make sure that you all who potentially may be either current Stata users, or maybe you're dipping your toe in the Stata waters and want to know how to utilize Stata for your fiscal needs. And so I'm going to kick it over to Chuck, but please know that myself and Margaret, you see there in the box, Margaret Arrow, will be managing the chat. So feel free to either come off mute as Chuck is talking. He is one of those folks who is happy to take questions as he goes along, and or you can put things in the chat and we can flag them for him as well. Additionally, and I know who mentioned this, there is a link in the chat where you can get all of the slides and data sets and do files that we will be using. And this is one of my favorite topics, which is multiple imputation. I am a missing data nerd. And so I always love this and love to see how it's updated. So without further ado, I'm going to turn it over to Chuck. Thank you, Chuck.
Thanks, Jenny. Can everyone hear the audio okay? I've updated my audio system. It sounds okay? Okay, good.
Yes. Oh, and then Chuck, can I do one more thing? Please note that we will be putting a link in the chat at the end of the today's workshop to get your feedback. So please, please, please fill that out. It helps us a lot. Okay, that's it.
Okay, cool. Thanks, Jenny. Okay, I'm going to share my slides real quick here and whoops. I clicked on something wrong. Hang on just one second. There we go. Um, and as Joni mentioned, I did paste a link in the chat window to the slides. Can everyone see the slides okay? I'll take that as a yes. So today we're going to be talking about multiple imputation using Stata. As I just mentioned, I pasted this link into the chat window so you can just click on it and go grab all the slides, the data sets, and the do files. And so you'll have all of that and be able to reproduce everything in here. So here's what we're going to cover today. So I'm going to talk a little bit about an example data set, and then we have to talk about missing data mechanisms because it makes a difference as to whether or not multiple imputation is appropriate or not. And then we'll talk about the idea and the concept of multiple imputation. And then I'm going to show you how to do it using Stata. And then we'll come back at the end and talk a little bit about why. We'll talk about why along the way as well. But as Joni mentioned, if you have any questions along the way, please feel free to just unmute your microphone and jump in. Gives me a chance to grab a sip of water and rest my voice. So please jump in at any time. So here's the little example data set that we're going to be using today. I call it the heart data, and it's included in that download. And it includes the following variables. We have a binary variable for attack. It's an indicator for whether or not a patient has a history of heart attack. And then I have a variable called smokes, which is an indicator for whether or not the patient is a current smoker or not. Then we have age measured in years, BMI, which is body mass index, female, which is an indicator for female or not, and then HS grad, which is high school graduate or not. I don't think we actually use that much. But anyway, those are the variables that we're going to be using. And again, it's available in that download. So the objective here is to examine the relationship between smoking and heart attacks. We speculate that there might be some relationship between smoking and heart attacks. Very cutting edge research here. And we want to adjust for age, body mass index, educational status, and gender. So to do this, we want to perform a logistic regression model for the binary dependent variable heart attack or attack, and use the other variables as regressors. So the first thing I always do with a new data set is I use the summarize command to just summarize the data. And the first thing I look at is the obs column. And the reason I do that is because that obs column often dictates the entire rest of the analysis. Because as I scan down the obs column, I see that I have most of the variables have 154 observations, but BMI has 132 observations. So I have some missing data in my data set, and I want to include BMI in my logistic regression model. So I'm going to have to take that into account in my modeling strategy. I'm going to have to do something with that, or at least acknowledge that I have some missing data. So if I were to list the raw data, these are the first 12 observations in the data set. Again, I have attack. It's just this binary indicator variable zeros and ones. The variable that has the missing data is BMI, and you can see the missing data in the raw data by a dot. In Stata data sets, it's represented with a dot. It's actually stored as you can think of it as positive infinity. It's the largest number that your computer can store. But you can think of it again as positive infinity. And so you have to be careful with that because if you say, I want to summarize the data for everyone with BMI greater than 10, it's going to appear in there because positive infinity is greater than 10. So you do have to be careful when dealing with missing data with data management issues like that. Anyway, so that's what the raw data looks like, and that's what the missing data looks like, these little dots that you see in the raw data. Well, let's see. So, how are we going to handle this? Well, one way, and people used to do this, would be to just ignore the problem. We have some missing data. So, let's build the model and away we go. And this is called complete case analysis. As far as I'm aware, all statistical software by default uses complete case analysis with their models. So, what that means is that if I want to fit a logistic regression model that includes the variables, the dependent variable attacks, as well as smokes, age, BMI, HS grad, and female, it's going to fit the model only using observations that have complete data for all of those variables. If any one of those variables has missing data for an observation, that observation will be kicked out. It only takes missing data for one variable to kick the whole observation out of the analysis. So if we look at the number of observations in the model, we see that there are 132 observations used to fit this logistic regression model. And the reason that it's not 154 is because of those missing values for BMI. Any of those observations are removed. Anyway, it's called complete case analysis. Now, remember, we're only wanting to adjust for BMI. What we're really interested in is the relationship between smoking and heart attacks. So here the odds ratio is 4.68. That's a pretty large odds ratio, no surprise there. But we've only used 132 observations. So what are we going to do about this? Well, in the old days, you could have gotten away with this. You could just do complete case analysis, mention it somewhere in the discussion, and move along. But in 2026, that's just not going to fly anymore. Not in most academic journals. So, what are our options then? Well, one option is something called mean substitution. And this is kind of a good place to start because it leads us into multiple imputation later. But again, in the old days, before multiple imputation was readily available in commercial software, this was a popular way to handle missing data. So, what we would do is take the variable BMI, estimate the mean BMI for the 132 variables, observations that we actually have, and then take that mean and substitute it in for any missing values of BMI. So here at the bottom of the slide, what I've done is taken the original variable BMI, I've copied it into a new variable called BMI underscore new, and in BMI underscore new, what I'm doing is substituting the mean for any missing values of BMI. Okay, so then I'll have complete data for BMI new, again with the missing values replaced with the mean. And this feels right. What could be wrong with that? If that's the average BMI, what could be wrong with substituting the mean? And in fact, if we summarize those two variables, BMI, the original variable, and BMI new, the one with mean substitution, if we look at these, the mean is the same for both variables out to 5 decimal places. So the mean is the same, the min is the same, the max is the same. Something feels right about this. But if we look at the standard deviation, notice that the standard deviation for BMI new is smaller than the standard deviation for the original variable BMI. So why is this? Well, if you think about, and someday I should put it in the slide, but I just kind of assume everyone remembers it. The formula for estimating the standard deviation is each observation minus the mean, square it, and then divide by the n minus one, and then take the square root of that. Anyway, that piece of the equation, the each observation minus the mean, that's where the problem occurs. If we're using mean substitution, the mean minus the mean is always zero. So even though we've completed the data with the mean, we're not adding any variability to it. And so we will always underestimate the standard deviation or the variability using mean substitution. And that causes other problems with p-values and things like that, confidence intervals down the road. And so it's a well-known issue, and that's why we really don't use it anymore. But it is a good kind of a starting place to start thinking about multiple imputation. Just for fun, let's run the model using complete case and mean substitution. So at the top is the model we fit before with mean complete case analysis using 132, and the odds ratio was 4.68. But at the bottom, I fit the model using mean substitution, and now the odds ratio is 3.3. Both of them are large. Both of them suggest that there is a strong relationship of some sort between smoking and heart attacks. But which one is correct? And there's no real way to know. There's no real theoretical justification for using either one of these. It's just kind of more one is convenient, the other feels good, but there's no statistical justification for either one of these. So it's hard to argue that either one of these is sort of correct in any sense. Okay. So that led over the past 30, 35 years to a lot of research into how to handle missing data. And so when you start thinking about how to handle missing data, the first thing we need to talk about are how did the data become missing to begin with? To begin with, and that's called missing data mechanisms. There are subcategories of these, but we're going to focus on the three big ones. First is called missing completely at random, or MCAR. It's often called MCAR. The second one is called missing at random, or MAR or MAR. And then the last one is called missing not at random, or MNAR. So what are these things? Let's go through and define each one. So if the data are missing completely at random, it means that the reason for the missing data is unrelated to anything in the data set. It's unrelated to the observed data that we actually have. It's unrelated to the unobserved data that we're missing. There's no relationship between missingness and the data itself. Okay, it's truly just random. So as an example, subjects may withdraw from a study for reasons like they just moved, or they moved away because their job moved, or maybe there were equipment failures that we didn't anticipate, or some sort of data recording errors. But the reasons for the missingness have nothing to do with the actual data itself. That's missing completely at random, or MCAR. I've drawn this diagram to help explain that, but I'm not sure it's terribly helpful, so we'll skip past it. So the next one is called MAR, missing at random. And that means that the reason for the missing data is unrelated to the missing data, the data that are missing that we don't observe. But it could depend on some of the data that we actually did observe. There could be a relationship there. And so the missing values are not just a simple random sample of all the data values. So, as some examples, study of blood pressure, the study subjects might withdraw from the study because of severe side effects caused by the high dosage of the treatment. It's not caused by high blood pressure itself, but it is caused by a side effect and we have information on side effects in the data set. Another one might be in a study of income. Respondents with lower education might be less inclined to report their income. So it's not the income itself that makes them not respond, but it's the lower levels of education that lead them to not respond. And low education or education status may be in our data set. And so we could look at the relationship between the low income and the missingness of the data. Okay. The last one, the third one, is called missing not at random. And this is where the reason for the missing data is directly related to the actual unobserved or missing data itself. So the most sort of common example of this is in a study of income. People who have very low and very high incomes are less inclined to report their income. So the reason it's missing, the reason we're missing income is the value of income itself. Okay. It's not related to other variables in the data set. It's we're missing income data. It's because the income was very high or very low. Another example is in a study of depression. People who are very depressed may be less likely to actually report that they're depressed. And so we might be missing depression responses because someone is very depressed. It's related to the missing data itself. And that's a big problem that we're not going to discuss here. There are ways of dealing with data that are missing not at random, but that's not a topic for today. If the data are missing at random, multiple imputation is not going to solve that problem. It's not going to get us around that. Okay. So one way of so MNAR, if we have data that we believe are missing not at random, then that's we're done, or we need to go somewhere else and read another book chapter on a different topic. But if the data are either MCAR or MAR, we can differentiate between those two. So one way to do this, and there's actually a user-written command in Stata that will do this, but just to see how to do it manually, what we're going to do is create another indicator variable in the data set for missingness of BMI. Okay, so I'm going to generate a variable called miss BMI, and it's one if the observation is missing BMI, zero if it's not missing. So if we were to tabulate this new variable, we see that 132 are zeros. That means they have complete data for BMI. And then we have 22 that variable equals 1. That means they're missing BMI. So the variable is an indicator for missingness of BMI. Then what we're going to do is use that indicator variable as the dependent variable in its own logistic regression model. So the binary dependent variable here is missingness of BMI. And we're going to include the covariates attack, smokes, age, HS, grad, and female. If we look down, I know this is kind of a misuse of p-values. We're doing sort of a fast and loose thing here, but if we just skim down the p-values really quickly, we can see that none of these are greater than, excuse me, less than 0.05. And we're not adjusting for multiple comparisons or any of that. We're just informally using p-values as a quick guide. And what this suggests is that the data are really missing at random. It's not, the missingness is not related to any of the other variables in the data set. Okay. So that's just one way to differentiate between those two. Okay. So any questions up to this point? This might be a good place to pause quickly. So again, if the data are missing at random or missing completely at random, multiple imputation can work. If you have data that are missing not at random, you're going to have to do something else. That multiple imputation doesn't work there.
I've got a question here. This is Robert Ravetti.
Okay.
Yeah, I assume you're differentiating between a missing variable and a missing case altogether.
Yes, yes,
Yeah,
yes.
and would there be entirely different methods for handling missing cases?
Well, that's what we're talking about here is missing observations, missing cases in the data set, not missing variables.
Well, I mean, in a row, you're missing one number in the row versus you expected to see an entire row and it's not there.
Oh, I understand. So, yes, and we're going to talk about that as a little bonus thing at the end if we have time. I put some bonus slides in here. We have a command in Stata called gsim that does something called equation-wise deletion, and it's similar to the pwcore command in Stata if you're familiar with that.
Hmm.
So the correlate command in Stata uses complete case analysis. So if you throw in 10 variables into the correlate and it creates the correlation matrix, it will remove the observation if it's missing an observation for even one variable. That's sort of wasteful when you're talking about correlation. So there's another command in Stata called pwcore, and it does sort of correlation wise or pairwise deletion. So if you're missing, say you have 10 variables and you're missing data for one of them, observations for one of those variables, it only affects any correlations that involve that one variable. But all the rest of the variables will use whatever data is available. And gsim works in a similar fashion, and I'll come back and show you that at the end if we have time. So yeah, good question. But the rest of Stata's commands are use complete case analysis. So yeah.
I have a question.
Sure.
Yeah, thank you so much. It's great. So one of the way that when we write the manuscript and describe missing data, what I have done before just to describe the pattern of the missing data. Let's say if the primary exposure was race ethnicity by race ethnicity, and you say we know a pattern, by race. So, but interestingly, what you showed that you could do a logistic regression and see if the p-value is significant. I guess my question is like for the future, um, how to say we assume missing at random and then so justify that. Should we say by the pattern or should we say we did the logistic regression and like how do you say it?
In this case, I would say I would first off list any missing data and then show that pattern. And then if you do a logistic regression, I would mention those patterns as well. Anything that sort of explains why the missingness came about. And I guess the fallback is always that it's just random bad luck. It's missing completely at random. But there may be occasions where you do look at the relationship of missingness with the other variables and see that okay, a certain race group you had more missing data, or a certain gender, or maybe older people or younger people, or it just sort of depends on fit the logistic regression model and see are there other variables in the data set that are related to the missingness itself, and then just report that however it falls out. Using that sort of p-value method is something that's I do, and I know a lot of people use as an informal metric for is there a relationship? You might want to be a little more formal about it, writing it up for a an academic manuscript, but I would just be just descriptive with the reader and explain how you ascertained that. Yeah.
And that's significant p-value. I see you listed the outcome and the primary exposure and the model. So is that where is the main focus? Because let's say you did like, median household income and became significant. Does it matter if the outcome and the primary exposure, the p-value was not significant?
I'm not entirely sure I understand the question, but are you saying does it, for instance, if you ran the model and in our case, smoking and heart attack were not significant, and then you uh, took the missingness into account and then it became significant, is that what you're talking about? Would you need
No,
to be
let's say the like mortality smoking, they were not significant, but then BMI was significant. Does it matter? Because BMI is just a covariate, it's not the primary exposure, it's not the
right?
outcome.
Right. I mean, it might be something to mention, but that would, and depending on the type of study you're doing, that would fall into the exploratory findings. It's not really the main primary outcome that you were looking at, but it is just something interesting to report as maybe a hypothesis generating result for the future, something to look into. Yeah.
Thank you.
Sure. Thanks for the question. Yeah, there's a lot more to these mechanisms because if you're we're only going to today we're only going to talk about missing data for one variable. When you start talking about missing data for multiple variables, then there are these far more complicated scenarios where there's something called monotone missing patterns, and that sort of dictates the methods that are available. That it becomes very complicated very quickly. So we're going to stick with just missing data for one variable today. Maybe someday I'll
Oh, it looks like Chuck froze for a moment. We'll just give him a second.
Okay, sorry about that. I don't know what happened, but I got the blue screen of death and then my computer rebooted. So, can everyone hear me okay?
Yes, we
Yes.
can hear you.
Okay, sorry about that. That has never happened before. Okay, let me get the slides back up again here and we will continue. Um, okay, hopefully the slides are back up. And we were just about to talk about what is multiple imputation. Okay, here we go. So essentially, there are three steps to multiple imputation. There's the imputation step, where we're going to actually impute the data, and I'll describe what all these parts here shortly. And then we're going to do the completed data analysis or estimation step on the completed data. And then after we do the analysis on each of the imputed data sets, we're going to pool the results into one summary result. So what does that mean exactly? So first off, let's get some notation and terminology under our belt. So I'm going to use the letter capital M to denote the number of imputations. By imputations, that means I'm going to make multiple copies of the entire data set. And for those of you who are wondering, there are more efficient ways to do this, and Stata will do them rather than making full copies of the entire data set. You can just make copies of the missing parts of them. But anyway, we're going to make copies of the data, and capital M is the number of imputations. So if capital M equals 5, that means we've made 5 copies of the data set, and we have the original as well. We're going to use little m as an index for which imputed data set we're referring to or working with. So little m equals 2 means we're working with the second imputed data set. By convention, most books and papers refer to m equals 0 as the original data set. And we're not going to touch the original data set. That's going to stay in memory untouched. We're not going to impute anything for the original data set. Only m equals 1 through m equals big M will have the imputations in them. Okay. So to make this a little more concrete, let's say that we have this data set, and on the left, I've taken screenshots of the data editor to sort of emphasize the idea that we have the original data set at the top, and then the middle, or the one below that, is m equals 1 is a copy of the entire data set with all the missingness and everything. Okay. And then the third one from the top, little m equals 2, that's a second copy of the data set. And then little m equals 3, that's a third copy of the data set. So we're literally going to make multiple copies of the data set in memory. Okay. So now let's take a look at the original data again. Imagine making that BMI new variable again, just like we did with mean substitution. And what I'm going to do then is fit a linear regression model for BMI. BMI is a continuous variable. We're going to assume it's sort of normal-ish, or at least has normal residuals. And so it's continuous. We're going to fit a linear regression model for BMI using the predictor variables attack, smokes, age, and female. Notice heart attack is in there. That's our main primary outcome, binary outcome of interest. Even it's included in the imputation regression. Okay. After I fit the model for BMI, I'm then going to predict the values of BMI. I'm going to create a new variable called BMI underscore pred. Okay, predicted. And that's going to be, we're going to literally use those coefficients in our model to predict the values of BMI, the expected value of BMI for given all the covariates in the model. So we're going to use those coefficients from the model. BMI new is equal to 26.6, that's the intercept, plus 1.7 times whether or not someone had a heart attack, minus 0.47 times whether or not the person smokes or not, minus 0.03 times their age, minus 0.31 times whether they're female or not. And so what I'm going to do is substitute that in only for the observations that are missing. Okay. There's no point in using the expected value for the observed data. It's kind of like doing mean substitution, but it's a conditional mean substitution. Okay. I'm just going to substitute that in. I should also emphasize that this is not literally how this is done. It's an analogy of how it's done. Okay. So it's sort of like using a conditional mean substitution. And so because each of the imputed data sets will then get the same expected value, it has kind of the same issue of mean substitution. They're all going to be so similar that the variance, it's going to underestimate the variability. So what I could do then, and again, this is an analogy, this is not literal, but what I could do is I could then throw in some random noise. Imagine calculating the variance of the error terms and then just throwing in some random noise from a normal distribution with a mean equal to zero and the variance equal to whatever the variance of the error terms is. Might be a strategy. Again, not literally what is done, but it's kind of an analogy. And what this does by throwing in a little bit of random noise, that means that each data set is slightly different. So the first imputed data set at little m equals 1, I might add 1.7 to an observation. The second imputed data set, I'm going to get the same conditional mean, but I'm going to throw in add zero point 0.9 to the value. The bottom one, little m equals 3, I might subtract 2.1. So what I'm doing is adding in some random noise to compensate for the fact that I've used the same conditional mean in each of those data sets. Okay. So each of the imputed data sets is going to have a slightly different value for the missing data. And it'll be unique to each observation. Each observation will get its own prediction in each of the data sets. Okay. So then what I can do, that's the imputation step. That's how I'm going to create the copies of the data and fill in or impute the missing data. Once I've done that imputation step with all the imputed data, what I can then do is estimate or fit the model for each of the data sets. So I'm going to take data set little m equals 1, fit my logistic regression model for the binary dependent variable attack. I'm interested in smoking, and I'm using my BMI new variable, which has complete, all the observations are being used because I've imputed the missing values. And I can do that same model, fit that same model for little m equals 2 and little m equals 3. So I'm going to fit that model for each of the imputed data sets separately using the imputed data sets. Then what I'm going to do in the pooling step is I now have within data set or within model variability, and then I have between variability, between data set variability as well. And I'm going to use something called Rubin's rules to combine the results into one summary result. So it takes into account the between and within data set variability. So I get an estimate of the total variance. And it's a matrix, and it takes into account the standard errors for each of the covariates in the model. So that's kind of the idea behind multiple imputation. Don't take that too literally. It's actually much more complicated than that. But in a sense, it's sort of like making copies of the data, estimate a conditional mean for each of them, and then throw in some extra noise. Okay. Any questions about that so far?
Chuck, I had a quick question.
Sure.
You said that it's like estimating conditional means. Is there some theory, or is it more based off of like, prior literature that you would make the assumptions around the conditional mean to which you would add the noise to these duplicate data sets? Like how would one approach that?
Right. I guess first I would say don't overthink this too literally because this is not literally how it's done. It's way more complicated and involves empirical Bayes and other things. So it's not literally done the way I'm describing it. But it's so much more complicated that it's easily a 2 or 3 day short course on how that's done. But the conditional mean part is just that's what linear regression is. It's just estimating conditional means. So for example, in this bottom of the slide, the person at the bottom of the data set here, their expected systolic blood pressure is 26.3. That's a conditional mean. It's conditioned on their value of heart attack, their value of smoke, their value of age, their value of female. So it's an empirical conditional mean. It's the expected BMI given their value of attack and smokes and age and female. So that's how I'm using the term conditional mean in that sense.
Thanks for clarifying.
Yeah. But again, don't overthink this too much and don't go telling your colleagues, oh yeah, all you have to do is make copies of the data set, run some regression, and then fill in some noise. That's not literally how it's done. I've long been curious to actually do this just to see how it would compare with the way it's actually done because this would be a lot simpler. But I'm just too lazy to do it. I have too many other things to do to dabble in the theory or whatever of multiple imputation. But good question. Any other questions before we move into how to do this?
Chuck, I'm responding to a couple of these in the chat, but I would love
Yeah.
your perspective too. There
Okay.
are two questions. One was, can you please break down how to find out if the data is missing at random or MCAR? And then the second was, what is the maximum missingness we can handle using multiple imputation? I gave an answer to that, but feel free
Yes.
to expand or give your perspective.
I think you've heard my story at least once or twice about my student I had. I'll tell that story again here in a second. First question is, how do you tell them apart? There really is no empirical way to tell them apart. Well, that's not entirely true. MNAR, there are ways for testing for MNAR, and I don't want to go too far off down that rabbit hole because that takes us over to something called Heckman selection and endogenous variables and things. And so diagnosing data that are missing not at random involves some things that we haven't talked about today. But there are ways that econometricians, and especially James Heckman, have developed for diagnosing and dealing with data that are missing not at random. So I'm going to punt on that one. The other two, missing completely at random and missing at random, the only thing I'm aware of, and someone please correct me if I'm wrong or if you know of other cool modern tricks that I'm not aware of, for differentiating between completely at random and missing at random is that little logistic regression trick, where you look to see, you basically create an indicator for missingness and then fit a logistic regression model and see if other variables in the data set are related. And it may be so simple as descriptive. Like someone asked the question earlier, what if race? There may be certain race groups where you have more missing data among certain race groups than others. Does that have any meaning? Does it have any impact on the results? I don't know. You'd have to speculate on that as to the meaning of it, but it'd be easy to identify, is there a relationship between any of the other covariates and the missingness?
Yeah, I'd agree with that. I'll also add that on top of that, I'll give my epidemiologist perspective, which is if you find associations, you do want to think about why they might be, right?
Right,
You want to have a theoretical framework for like why potentially in my data set, why might I have found these particular predictors.
right,
I think later on you probably talk about auxiliary variables, right? So why you might potentially want to use those in your multiplication. Because what you don't want to do is just sort of throw stuff into multiplication model without having a good justification for that. What
right.
you want to do. So it's really kind of it's a both and question.
Right. I'm really hesitant to use this example because I hope it's not in any way, shape, or form offensive. That's not how I mean it, but it's so obvious. If you ask a question about U.S. citizenship on your survey, you have a survey and you ask about, are you a U.S. citizen or not? I just had to do this yesterday, filling out a jury duty form. Are you a U.S. citizen or not? I'm going to guess that certain ethnic groups may respond to that question differently than other ethnic groups. I hope I'm not being too political or offensive with that, but it's such an obvious example these days as to why certain groups may or may not respond to a question. So yeah,
Agreed. I mean, it's similar to asking about nativity, right? So it's all
right,
similar
yeah,
pieces of information.
yeah,
And then the second question was, what is the maximum missingness we can handle using multiplication? Um,
okay,
the response
yes,
I gave, if this helps you, is I know because it's complicated. I said that technically there is no exact answer for this. I said it depends on the missing data pattern, the missing data mechanism, and the quality of predictors of missingness. I
yes.
said, and then I said, if you have a lot of missingness, there are some features of the multiplication that you can use to help improve the imputation model and improve the estimated variances.
Yes, I totally agree with all of those. It depends on a lot of things. The biggest influence is probably, do you have good variables that are predictors of the missing data? Because if you don't, it doesn't really matter if you have a little or a lot missing. If you don't have good predictors in your data set of the missing data, then you're not going to be able to recover it. Because multiple imputation relies on information from other variables in the data set to predict that missingness. So, for instance, BMI. If you know someone's age is probably a pretty good predictor of BMI. So if you include it in an imputation model, there's information about BMI contained in age. And there's information about BMI, maybe in terms of gender. I don't know. But if you look at handedness. Are people left-handed or right-handed? And that's all you had in the data set. You're probably not going to do a very good job of imputing BMI because there's just, I'm guessing, no information about being right-handed or left-handed and predicting BMI. Um, two very short stories about that that shocked me, and maybe it'll shock you. I don't know. But about 20 years ago, I was working on a project with the fatal accident reporting system data, the FARS data. Anytime there's a car accident in the United States, if there's a fatality of any kind in the car, a pedestrian, that must by law must be reported to the federal government, and it goes into the fatal accident reporting system. And we were doing a study using that data set, and one of the variables we were using was blood alcohol level. Now, you would think that you would have complete data or near complete data for blood alcohol level, the percentage of the driver. But in fact, they only had complete data for 20% of the sample. Now, it was a huge sample. It's on something on the order of 10,000, 15,000. I can't remember. It's a big data set, not big like Amazon big, but good sized data set. But we had missing data. We were missing data for 80% of the blood alcohol level data. And because it's a federal data set, they had already imputed this. They had already created the imputed data sets for us. And we were simply given instructions how to do the analysis, taking that imputation into account. This is 20 odd years ago. And so when I saw that, I was horrified. I thought, no, you can't impute 80% of the data using 20%. That's absurd. On its face, it sounds completely absurd. But it was a federal data set, and they had a whole panel of experts that supposedly had done a good job imputing this and blah, 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 blah. So the investigators convinced me to go through with it. So we did. But it kind of always haunted me. So years later, I don't know, 8, 10 years later, I had a graduate student who was very interested in multiple imputation. So I said, okay, I have a good study for us to do. Let's create data, complete data, and then knock out 10%, 20%, 30%, all the way to 90% under various conditions, and see, using multiple imputation, how well does multiple imputation perform, uh, depending on how much data are missing and other factors. And I was genuinely shocked to see that you could go up to about, if you had a reasonably large data set with predictors that were related to the missing data, you could use multiple imputation to accurately get accurate results up to about 80, 90%, 80 to 90% missing. Now, again, that depends on those other factors Joni just mentioned. It doesn't work all the time, but it can work in a good scenario if you have good predictors. So, for instance, the missing blood alcohol data, you can use things like, there are several things that predict that very well. First off, is it a single car accident? Was there one car and one driver involved? If there was, that's a very good predictor of blood alcohol level. What was the time of day? If the time of day is somewhere in the range of 2 a.m. to 4 a.m., there's a very high likelihood they had high blood alcohol level. Being male was a strong, and being male in a certain age range, I'll let you guess what the age range is, was a strong predictor of blood alcohol level. So we had good variables in the data set that predict missing blood alcohol level. So that's maybe a long-winded answer to that question, that it depends on the quality of the data you have to predict, but it can be used to predict a large amount, way more than half of the missing data. So hope that answers that question.
I also was going to add that you sometimes see these high levels of missingness for planned missingness, if people are familiar with that.
Oh,
So,
yes. Yeah.
for those of you who may not familiar, it's often common for very large, particularly national data sets, to do planned missingness. So, for instance, if there are laboratory values that are really expensive, they may only collect that data on a proportion of the population to save money, and then they'll use imputation to fill in the rest. So there are examples of that that are intentionally done as well. So it's really missing, it's missing completely at random because they'll randomly sample out of that population. And so then you're able to do the imputation as well.
That's an excellent point. Yeah. Todd Little at Texas Tech has done work on doing long questionnaires. You know, when you have these questionnaires that have like 100 questions, there's a phenomenon called questionnaire fatigue. After about question 30, you just get tired and you don't want to answer 100 questions. So they'll do the same thing, planned missingness, where they'll do subsets of the questionnaire for different people with lots of overlap among them, and then correlate those or use multiple imputation for it. Thanks for pointing that out, Johnny. Okay, so why don't we move on and see how we're going to do this in Stata. Are we going till 1:30 today, or are we doing 90 minutes or 60 minutes today?
I don't remember. Margaret, what did we have it calendared for?
I believe it was 60 minutes.
Okay, I'll move quickly. We're almost done, but doing this is so easy in Stata that I'll move kind of quickly so we can wrap up. We lost a little time when my computer decided to reboot. So, okay, so this is surprisingly easy to do in Stata. There's a suite of commands that would begin with mi for multiple imputation. So one of them is called mi impute, one of them is called mi estimate, and then there's some others. If you're worried and thinking, oh, how am I going to get through all of this? Let's just jump ahead to the control panel. There's actually, it's like a super dialog box. It's a big control panel with buttons on the left-hand side, and it walks you through the steps of doing the multiple imputation. So if you click at the very top, you click on examine, it'll show you some things to examine the data. It'll look through your data set and identify variables that have missingness, how many patterns, things like that. And then set up, impute, import, manage, estimate, test, and predict. And we'll go through these as we do this. So first off, we need to examine the
Oh, hey,
data.
Chuck. Sorry not to
Yes.
interrupt. We advertised today's as 75 minutes, so it's meant to go to 1:15 to allow for questions.
Okay. So we have a little bit more time. Okay, good. Thanks. So the first thing we need to do is examine the data. So that command, if you're curious, is called mi miss table, and what it will do is report the counts of missing data. Now, our data set is simple. It only has one variable that contains missing data, but often it's more realistic that you would have 4 or 5 or 6 variables that have missingness, and that becomes way more complicated. So again, the commands are going to be mi set f long and mi miss table summarize. That f long, mi set, you can either have your copied data set stack one on top of the other vertically, or you can do f wide, which stacks the variables or the imputed data sets to the side in your data set. I don't think it really makes any difference, and I don't know why that's a thing, but it is. So there's just multiple ways you can include the imputed data in your data set. Okay, so mi miss table summarize. So it's going to tell us the number of observations that equal dot. That means missing. So we have BMI has 22 missing values, nothing greater than that, and then we have 132 that are not missing. And then it tells us the number of unique values. So that's kind of a clue that this is a continuous variable. And then we see the min and the max. Okay. And there are other ways if we had multiple variables, multiple missing variables to look at patterns among them, but we're not going there today. It's much more complicated. So the next thing we need to do is actually impute the data. So we can click on that impute button on the left-hand side of the control panel, and then that gives us a whole bunch of choices. The way you go about doing the imputation depends on the kind of variable that you need to impute. And there are lots of options for this, and we don't have time to go through all of them, but just so you're aware, BMI is a continuous variable, so we're going to use linear regression for doing the imputation. There's another method called predictive mean matching for dealing with continuous variables that have missing data. Then there's also truncated regression for continuous variables with a restricted range. So if you had something like GPA that's bounded between 0 and 4, you might want to use that. But then there's also things like interval regression for censored continuous variables, logistic regression for a binary variable. So what happens if you have hypertension, yes or no, and you have missing data for hypertension? There are ways of doing the imputation step for binary data that has missing data. Same thing with ordinal logistic regression. If you have ordinal data, multinomial if you have nominal data, and even Poisson and negative binomial if you have count data. So those are your options for imputing different kinds of variables that contain missing data. The multivariate stuff is at the bottom. I just want you to know that it's there, and there are lots of, the three biggies, options for imputing multiple variables simultaneously. And that's way more complicated. Anyway, but it is possible to do that in Stata. We're just not going to talk about it today. So what we're going to do in this dialog box then is we're going to select the imputed variable. That's the dependent variable in our imputation regression model. So the imputed variable here is BMI, and then the independent variables or predictors of missingness, or excuse me, predictors of BMI are going to be attack, smokes, age, HS grad, high school grad, and female. Okay. So that's the regression model that we're going to use to predict BMI. And then below that, you see a little box here that says imputation. So I can check this box and then add as many imputed data sets as I want. The default value is 20, but I'm going to use 5 just to make it a little easier to fit into a slide. You would never only use 5 in practice. The minimum, the default we use is 20, and the courses I've seen, that's the kind of the absolute minimum you would want to consider. Modern computers, and depending on the data set, the size of the data sets you have, anywhere between 50 and 100 might be a better choice. But 20 is the default. We're going to use 5. You also need to specify a random number seed because we're going to be generating random numbers in the background doing the imputation step. So we can specify a random number seed so that we can reproduce these results in the future if we need to. Okay. So that's the mi impute regress command. Okay. And again, everything past mi impute looks just like any other regress command other than the add and random number seed part. But it looks just like any other regress command. It just has mi impute in the beginning of it. So then we're going to see a report of the data that was imputed. So we're going to see 132, for BMI, we have 132 complete observations, 22 incomplete observations, 22 were imputed for a total of 154 for BMI. It also tells us the number of imputations total and the number added. Now that seems a little weird. Why would they? Seems like they'd always be the same. You can actually add more imputed data sets later if you want to. So you might have already had 10 and you want to add 5 more. And so you could rerun this command and add another 5 to the 10 you already have. So you can run this more than once if you need to. Okay. So when you run mi impute followed by whatever kind of regression you're using, that's going to create 3 new variables in the data set. Underscore mi id, underscore mi underscore id, underscore mi underscore miss, and underscore mi underscore m. So let's start with underscore the last one, underscore mi underscore m. Remember we talked about using little m to index the data sets. If I tabulate that variable underscore m, I'm going to get 6 values. Underscore mi underscore m can equal 0. That's the original data set. And then I have 1, 2, 3, 4, and 5. Those are the copies of the data set. So I have 5 additional copies of the data set in memory now in addition to the original. So that number is indexing this underscore mi underscore m. That indexes which imputed data set does that observation belong to. Because if you keep scrolling down in the data set, there are going to be lots and lots and lots of these. So that keeps track of the data set. And then underscore mi underscore id, that keeps track of the ID within each imputed data set. So there's going to be ID1 for data set 0, ID1 for data set 1, ID1 for data set 2, all the way through 5. Okay. So it's there just as an accounting thing. It needs to keep track of which observation is now going with which data set. The other thing that we're going to need, underscore mi underscore miss, that tells us, excuse me, that tells us in the imputed data sets which observations contain missing data for BMI. Well, that's obvious in the original data, right? It's going to equal 1 if the data are missing for BMI. That's obvious in the original data set because it's still missing, but in the imputed data sets, there will be a value there. So the only way in the imputed data sets down below to know that a value is imputed is to look at this indicator value for underscore mi underscore miss. Okay, so those 3 variables are really there for Stata just to keep track of things. You really don't need to use them unless you're just curious. Now, one thing that you might want to do is you may need to do some data management along the way. And this can be a real pain because once you've already imputed the data and you need to do data management, you now have to do it on all of the data sets, data set by data set. So let's say you have age and you want to consider age squared. So you have to create a new variable called age squared. There are ways to do that with the already imputed data sets. There's even something in here for reshape. So if you needed to reshape your data that's already been imputed, there's a reshape version, there's a version of reshape for dealing with imputed data. So I'm not going to go through all of these, but just be aware if you click on management, there's a rich suite of data management commands for data that have already been imputed. Okay. Now, something that's a generally good practice to do is to go through and summarize the data for each of the data sets individually. So remember, m equals 0, that's the original data. Little m equals 1, that's the first imputed data set. Little m equals 2, that's the second imputed data set. So I can do this by typing MIXEQ or by equation colon summarize BMI. And what I can do then is just kind of glance down the data to look and see, do they look relatively similar to the original data? Okay. Obviously, we expect to see 154 observations, but do the means all look pretty similar to the original data? They're all right around 25 point something. Okay. Standard deviation for BMI and the original data set was 4.02, and that only used the observed data, obviously. And if I look at the standard deviations in the other data sets, they're all pretty close. They don't need to be exact, but they're reasonable. They're not like 15 or anything like that. Same thing with the mins and the maxes. In this case, they all turn out to be almost exactly the same. You don't see anything wild out there. If you do see one of these that seems very out of whack, again, the goal here is not to perfectly reproduce data, but you just want to make sure you don't have anything that's wildly out of whack. Like one of these doesn't have a mean of 35. If you did, you could delete that and then add another imputed data set. Go back and run that impute, add one, delete one. You could delete one of them first, or you get in your do file, just go through, change your random number seed and rerun your do file and then check it again. But it's just a good idea to peek at this and see, does it look reasonable? Now we're ready to do the estimation step. So, and this is really amazing to me. Almost every major regression command in Stata works with multiple imputation. So in our case, we want to fit a logistic regression model for the binary dependent variable heart attack. And we're going to include the variables smokes, age, BMI, HS grad, and female. Notice I don't have to put BMI underscore new in here. All of that's happening in the background. I don't have to mess with that. So I just put in the regular variable BMI and it will handle everything. Just to peek at this dialog box here on the left, look at where that slider is way up at the top of the box here. Multiple imputation works with just about every command, every regression command in Stata. So there's really no reason not to use multiple imputation anymore. It's really simple to do for all kinds of models. Okay. So if I click OK, the command is going to be MIEstimate colon followed by whatever the command I wanted to run was. So the syntax here is really simple. If I just wanted to fit a logistic regression model, I would just type logistic attack followed by the covariates. In order to use the imputation data sets, I just type MIEstimate colon in front of that same command, and it just handles everything for me. It tells me the number of imputed data sets, the number of observations, and there are lots of numbers in here we're not going to go into today, but essentially it's used Rubin's rules to combine the results across all of those data sets into one set of results. And the main thing we're interested in this case would be those coefficients, which in this case are the logistic regression coefficients, and you would need to exponentiate them to turn them into odds ratios. Not sure why. I asked once, and there is a reason why using MI that logistic reports coefficients, but you can transform them. Now, if you wanted to test something, obviously when you do a test, you're testing across multiple data sets. So again, you have to use those Rubin's rules to combine the results across. It's going to do the test for each of the data sets and then combine them. So there's a test button here in the imputation. You can't just use the regular old test command like you would in Stata. You would need to click test and then use the MI version of that. So, and there's a test syntax here where it gives you lots of choices. You want to test that the coefficients are 0 or that they equal some specific value or something else. Okay. So instead of just typing test BMI, we would type MI test BMI. And what that's doing is testing whether or not that coefficient for BMI is equal to 0 or not. And it's going to report an F statistic and a p-value from that F test. Okay. So, and that's testing whether or not that coefficient for BMI is zero. It has nothing to do with the missingness anymore, other than it's using the multiple imputation engine to do all of this. Finally, if you wanted to predict some, well, we're not going to go into that today in the interest of time.
Oh,
So anyway,
sorry, Mark, Chuck, you cut out for a second. Can you repeat your last couple of sentences?
oh, okay, sure. Sorry about that. So test, the main thing I was pointing out is that test, you can test lots of different things. BMI equals zero, BMI equals a specific value, but that's testing that the BMI coefficient equals zero. And rather than reporting a T like you would normally expect, it's going to report an F statistic and a p-value from that F statistic. And then if you wanted to generate predictions from the model, you can do that. We're not going to go into that here today. But there is a button here. It says predict at the bottom, and you could generate predictions from the model and using the imputed data. Okay. So that's the imputation control panel, and it really does walk you through the steps. So the first time you do this, I would suggest using this control panel. Once you get used to it, it's pretty quick and easy just to type the commands. But yeah, I would strongly suggest using that. So why? Why are we even doing this? I guess the cynical or sort of crass answer to that question is because you cannot just ignore it or do mean substitution in 2026. Your paper is never going to see the light of day in an academic journal. So, but again, the main point to emphasize here is that the object is not to predict the missing values as accurately as possible. That's not what we're trying to do. What we're trying to do is impute multiple data sets, multiple values across multiple data sets in such a way that it results in valid statistical inference. What was the original question we were asking? If we had complete data, what's the answer do we get? And if we use multiple imputation with missing data, would we get the same results? Okay. Now, another question you might ask is, well, why are we using this instead of other methods? There are other choices for this. We could use fully parametric methods. There are purely Bayesian methods for handling missing data. There's FIML, which we'll talk about in a moment, full information maximum likelihood. There are other things we could do. Why has multiple imputation become so popular and kind of become the default? The main reasons are that it's very flexible. It works for all kinds of models, as you could see in that dialog box. It works with linear regression, logistic regression, Poisson regression, negative binomial. It just works in so many different areas, and it's relatively easy to implement in software. It's not specific to one model or one data set. So it's very general and flexible. It can be more efficient than list-wise deletion or complete case analysis, and it can possibly avoid biases. So let's say that you ignored the missingness. There may be, when you run the results, you may get certain biases because of the missingness. And when you use multiple imputation, it can remove that bias. And there have been studies that have shown this. And it can be more efficient in the sense that you're using information from the other variables to fill in the missingness, which gives you more information or squeezes more out of the data set that's already there. Okay. Okay, I think that's enough about that. This has been shown over and over again in multiple papers over the years that it does yield statistically valid inference. And so, I remember when I first started seeing these papers in the mid 90s. I have to admit, I was a little skeptical. I thought, especially if you're imputing 20, 30, 40, 50% of the data, it's, the first time you see this, it's kind of, I think, natural to be a little skeptical, but there are loads of papers now that this is a very mature field, and it's been shown many times that this works very well. Assuming you have information in the other variables for the imputation. One of the things you need to remember to do is set the random number seed. Because if you don't, this is a stochastic method. We're generating random numbers. And so if you don't remember to set the random number seed, the next time you run your imputation, you're going to get different results. And so make sure you set the random number seed. It does preserve all the data, and so it can be more efficient. We already talked about that, and I need to update these slides. Anyway, so that's multiple imputation. I think we're almost out of time, and so I wanted to show you a couple of things really quickly, just some other ways to go about this. People who work with structural equation modeling a lot, uh, multiple imputation doesn't work with SIM, and that's intentional because the structural equation modeling people use a different method for dealing with missing data. and it's called Full Information Maximum Likelihood, or FIML. And that is available in Stata's sim command. So when you type the sim command, at the end of it, you would use the option method MLMV for maximum likelihood with missing values. But it's just using FIML in the background. So that's how you would handle missing data with the structural equation modeling command. Now, this part still blows my mind that this can be done. Survey works with both multiple imputation or FIML. So if you have survey weighted data, you can do this. You can do multiple imputation that I just showed you, or you can do full information maximum likelihood with survey weighted data. So you just put the SVY colon, once you survey declare your data, you just put the SVY colon command in front of your sim command, use MLMV, and you're doing FIML. And it's similar with multiple imputation. Now, I mentioned equation-wise deletion. Actually, I'm going to go through and show you how to do these. So if I were doing sim, let's say that I have glucose and insulin in a data set, and they're missing a lot of data. So I have HbA1c, age, BMI, I have about almost 6,000 observations. But two of these, glucose and insulin, I'm missing a lot of data. I can use the sim command with that FIML option, and I bump my model from 2,500 observations to almost 6,000 observations simply by using that method MLMV. So that's how you would do that with sim. Okay, just as a quickie observation. The example may not make sense, but the command is, simply, if I run this with sim by itself, I have 2,500 observations. If I run sim using the method MLMV, it's going to use full information maximum likelihood, and I'm now using almost 6,000 observations for the same model. Okay. And again, it also works with the survey prefix, so I can put that in there. I have been told by the person who teaches, we actually offer a course on survey. Excuse me, I teach the survey sampling course. The person who teaches the multiple imputation course at Stata has told me that I really should stop showing people how to do this because no journal would allow you to do this. But as a novelty, someone asked earlier about, are there commands or ways to deal with this where it uses all the data rather than doing case-wise deletion? This does something called equation-wise deletion. And so this is how you do it. With GSIM, GSIM is like SIM, but it's generalized structural equation modeling. And you can think of it as an extension of regression. So let's say that I'm interested in HbA1c as the dependent variable. And again, I have glucose and insulin in here, and they're missing a lot of observations, half the observations. A way to do this, and again, maybe I shouldn't recommend this, is you can clone the outcome variable, the dependent variable, just make an exact duplicate of it. And then when you fit GSIM, run two separate models. One model using the original dependent variable, using the variables that have complete data, and then on the other, fit a model, a separate model within the GSIM command, because it's going to run the whole thing simultaneously, using the cloned variable. So it's the same variable, just with a different name, and then include the variables that have the missing data. And if you look at the output, what's going to happen is the top model, this is like a multivariate regression style model. The top model contains 5,406 observations. The next model contains 5,381, and then the total number is 2,531. But somehow it's mixing and matching whatever is in here to squeeze the most information out. It's using the pairwise relationships between the variables in order to get the most out of the existing data. Rather than doing case-wise deletion, it's doing equation-wise deletion. Okay. But again, I'm told that's probably not a good thing to do if you plan to submit it to a journal, because they probably won't accept it. Anyway, but it, just so you're aware, something like that can be done. Two really good books on this topic. One on the left is called Applied Missing Data Analysis by Craig Enders. I've never met Craig Enders, but we've have kind of, anyway, I don't know him. I don't know him well, and I don't get any kind of kickbacks from his book, but it's a very, very well written book. Probably one of my top 5 favorite stat books of all time. It's just really well written. Anyway, highly recommend it.
Agreed.
The other one,
I was going to say that's my favorite missing data analysis book.
yeah, it's actually in its second edition now. That's the old first edition cover in the slide, but there's a second edition, and I liked it so much I even bought the second edition when it came out. I have both. So, Um, and then the other one, multiple imputation and its applications, the one on the right, that's by Carpenter and Kenward. I again don't know Mike Kenward well, but my former student that did his master's thesis with me went on to do his PhD with Mike Kenward at I think he's at University College London. He's somewhere in London. I forget exactly which university, but this book is also really, really good on multiple imputation. I've recorded some videos for the YouTube channel, so if you want to see me walk through, actually do this instead of talking about it, I actually point and click and do this stuff. There are videos up on the YouTube channels, and there are links to them here. So that's what I have for you today. If you have any questions, I'm happy to hang around, or you can email me later. Again, you can download all the material at tinyurl.com/multiple imputation. So that is what I have for you today. Sorry again about me getting that blue screen of death. That's never happened to me before. Well, I've done hundreds of these, and that's the first time. So
I have a question. Um,
okay.
what proportion of missingness you have to be worried about? For example, I use like 3% or less. I'm not worried. I can use complete analysis, but at what's the magic number you say, no, 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 you have to do like, missing imputation.
Yeah, I don't know that there's a universally agreed upon number. It probably differs from reviewer to reviewer and editor to editor in academic journals, but my guess would probably be somewhere around 5% maybe. One of the ways I've often seen done for answering that question is to do what some people call a sensitivity analysis. Sorry, I'm losing my voice. Is to run the model without it, do it with multiple imputation, and then if the results don't really differ, then do it the simple way. Just use complete case analysis and be done with it. Because in that case, you're not really gaining anything by using multiple imputation. But usually, journal reviewers are going to want to see that you took the issue seriously. And I think that's maybe a bigger thing that if you had 4% missing and you tried it with and without multiple imputation, they're going to be more comfortable thinking, okay, this person took this problem seriously, checked it. And whereas if you had 3% missing and you just ignored it, they might ask about it. 3% is a very small number and you could probably ignore it. But I'm not aware of any actual number. Does anyone have a number they want to throw out?
I made a joke in the chat and I said, sorry to break everyone's bubble, but in general, there is no magic number for most statistical techniques.
Yeah.
Yeah.
I don't know. I don't know about
I mean, I've
everybody else.
heard people
Joni sounds
say,
very,
I've heard people say 5% missing, but I just think that's an arbitrary thing, like p-value of 0.05. Like I don't
yeah.
know that you can ever really say that about any of this. So
It's very arbitrary, right? And it's always a nice round number, like 5%. It's not 4.732% or something like that. Any other questions?
I was just going to say, I did put a comment in the chat about using one of the diagnostic values you get from imputation, FMI. In Craig Ender's book, he recommends using that as a measure, a rule of thumb on how many multiplications to do. So if your fraction missing information is really high, then if, say it's 40%, then that sometimes indicates like try to do at least 40 imputations. So I put that in there as kind of a rule of thumb.
Yeah, there's way more to this than what I showed you today. And we have a really good course. Megan Kane at Stata Corp teaches like a 2 or 3 day short course on multiple imputation. And I sat through it a few years ago and it was really, really good. I learned a lot sitting through it. And it goes into far more detail than what this little hour workshop does. And it also does talk extensively about dealing with multiple variables, where you have missing data in multiple variables, which is way more realistic. Rarely do you just have one variable with missing data. So, by the way, I did wear my UC Irvine hoodie like always.
Woohoo!
Woohoo! Any other questions?
Just a quick one. Can we really impute our outcome variable?
I'm sorry, I'm getting some sort of static. I thought it was just Joni, but it's everyone. Could you repeat the question? I'm sorry.
Can we impute or should we impute the outcome variable, the desired outcome we are working on?
Okay, that's an excellent question. And I hear different opinions on that. On the surface of it, it sounds kind of absurd because if I'm going to impute data in the outcome variable and then turn around and probably use those same variables to fit the model, there's something that seems kind of circular about that. And so I've heard a lot of people say that's generally frowned upon. I've heard a minority say that, yeah, why not? So, Joni, what's your opinion on that? I hear,
Well, I say at minimum, even if if you make the choice not to use the imputed values for your outcome, you still want to include it in your imputation model. Otherwise, you impute variables that are uncorrelated with your outcome, which general is not is poor practice for imputation. Did I just echo?
yeah, you definitely want to include the outcome in the imputation model, but I think with your
But
question, if
but
the outcome variable is the missing data or
yeah,
has
I
missing data,
have. I'll tell you all this for my dissertation. I did, and that's because I had issues around missing not at random. So, but I had an outcome variable that was intimate partner violence that I needed to impute. And
Mhm.
so basically, what I did was a series of sensitivity analyses around my outcome variable. So I tried imputing my outcome. So I basically tried complete case analysis, and then I imputed my outcome. And then I basically did like a series of like sensitivity analysis where I tried to like um, I selected certain what did I do? I'm trying to remember now what I did, but I did a sensitivity analysis around my imputations where I said, hey, if I assume that 10% of my outcome is missing, or 20% of my outcome is missing, or 30%. So I tried different levels in order to assess like how much impact is using my imputed values having on my effect estimates. In my case, it had very little effect.
Okay.
So it was okay for me. But even if you read in Craig Ender's book, he says you can. His recommendation is that you can. But his recommendation is that you should be, and I don't know the middle room here, but there's something called auxiliary variables that you can include in your imputation model that are variables that are not of like inferential of interest, right? So they're not variables that you plan on using a regression model or etc., but they're variables that predict missingness. And so his recommendation is if you were to use the imputed values for your outcome variable, that you should include auxiliary variables that predict missingness in the outcome. So ultimately, you'll hear a variety of recommendations. So it is your choice. Like I said, again, in my example, in my case for my dissertation years ago, the majority of my missingness was in my outcome, which is why I made the choice and defended what I did. But ultimately, it's up to you. But I just tell people whether you choose to or not, just make sure it's in the imputation model always.
Yeah, thanks, Joni.
Thank you.
Any other questions? Okay, I'll take that as a no. So thanks everyone for being here. And sorry again about my little blue screen of death.
It's not your
And,
fault. Thank you, Chuck,
uh,
and thank you everybody for joining us today.
okay,
Please remember to fill out the survey, please. Um, Margaret put it in the chat. So if you have 2 minutes, please fill it out. We really appreciate it.
okay, thanks. See you soon.
All right. Thank you, Chuck. Uh,
Bye. Bye,
Pleasure
Johnny.
as
Bye, Margaret.
always.
Thanks.